Okay, good evening everyone and welcome to today's session, which is the 8th one for the course Introductory course in Real Analysis. So today most of the problems what we'll be looking at are based on continuity of function. Okay, so let's begin the session. Okay, so this is the question that was left in the last class. So I'll first try to address this problem and then I'll go to the new problems. Okay, so we'll start with this problem. So over here what you have been given is that suppose you have a function which is defined from, so over here a is some real number, okay, which is non-zero obviously. So a is a real number which is a is not equal to 0. Okay, so you have this function which is defined from open interval minus a comma a, and you eliminate 0 to this positive real line. Okay, and then it says that the limit x going to 0, f of x plus 1 by f of x is equal to 2. Then you have to prove that the limit is going to be limit of fx as x goes to 0 has to be 1. Okay, so one thing is clear, that if you assume that the limit, so suppose that the limit exists, suppose limit x tending to f, this exists, okay, and let it be L, so let it say it is L, then what we'll have is L plus 1 by L is equal to 2, and then you will have L square plus 1 is equal to 2L, and then from here you will get L minus 1 whole square is equal to 0, and this will give you L is equal to 1. Okay, so when you assume that the limit exists, then it's very easy problem. Okay, but here you have to first understand that how to make sure that this limit exists. Okay, so first goal would be to understand whether this limit actually exists or not. Okay, so since over here we have that this limit value, we have to prove that it is equal to 1, so we have to basically estimate. So the goal to prove this, we just need to estimate that this fx minus 1, is it less than epsilon if my x is very close to 0. So this is the question, you can ignore 0, right? So this is the problem what we have here. Okay, so let's try to understand how to establish this result. Okay. Okay, so the first thing is let's start with what has been given to us. Okay, so we have been given, so it's given to us that the limit x going to 0, f of x plus 1 by f of x is equal to 2, correct? So what does this mean? This means that for epsilon, okay, so before trying to prove this problem, we have to establish this one. Okay, so we have to first assume that some epsilon positive real number, right? So we'll assume that, so to begin, so let us write, let epsilon greater than 0 be any positive real number. Okay, and the goal would be, goal is to, so let me write in the next line, so the goal would be to show that this f of x minus 1 is less than epsilon if, I mean, there exists delta. Okay, I'll not write completely, but you can understand that there exists some delta such that if my x belongs to this interval, satisfy this condition, then fx has to satisfy this condition. Okay, so there should exist, so you have to find, maybe goal is to find delta greater than 0 such that we have this. Okay, so this is something that we need to establish over here. Okay, so let's start with this one. This has been given to us, so we'll try to use the definition of limit to get something. So since this limit exists and is equal to 2, so for epsilon greater than 0, I mean for this epsilon, so this epsilon I am taking, so for epsilon greater than 0 there exists delta greater than 0, delta naught, such that, so this f of x plus 1 by f of x and minus 2 would be less than epsilon if 0 less than mod x minus 0 less than delta 0. Okay, so this is, I have just used the definition of limit. Now from here what I can conclude is, so let's take fx as the LCM, then you have f square x and then minus 2 of fx plus 1 is less than epsilon if 0 less than mod x less than delta 0. Okay. Now from here what we can say is, so the numerator what we have over here is, this is f of x minus 1 whole square, and then in the denominator we have mod of fx. Okay, so that I am throwing on the right hand side. So let me write this as f of x minus 1 whole square is less than epsilon times mod of fx if 0 less than mod of x less than delta naught. Okay, so since here I am getting square, so I'll choose epsilon square. Okay, so see, this epsilon is something that we have chosen, and now I'm just taking to prove to use this condition, that limit. So I am choosing this epsilon square as my epsilon. Okay, so because due to this I will get some delta naught. So this is by definition, I should write. So this is by the definition of limit. Okay. Okay, so now we have got the reach till here. Now the point is that, again, like I have already mentioned this in the earlier session, that if we can say that it is bounded by something, then we are done. So suppose I get some c, then we are done, right? Then it would be easy. So now our goal would be to prove that this is bounded by some constant. Now for that what we'll do, again I'll use the definition of limit. Okay, so then for so let me say in this way maybe. So for epsilon tilde equal to this, and now I'll choose for epsilon tilde equal to 1. Okay, there exists some delta 1 greater than 0 such that, so again I'll use the same definition. So mod of fx plus 1 by mod of fx minus 2 is less than 1 if 0 less than mod of x less than delta 1. Correct? Again by definition. Okay, because by definition says for any epsilon you will get delta. So here I have chosen epsilon to be epsilon square. Okay, and here I have chosen epsilon to be 1. Okay, so again, like I'll try to proceed in the same. So what does this mean? This means that fx plus 1 by fx is less than 2 plus 1 3, and here I'll get 1, right, if 0 is less than mod of x less than delta 1. Okay, now what does this mean? So if you remember this condition, that your function f was positive, right? So that's why what I can say, that this is positive, correct? So I can say fx, just a second. So what I can say is, no, let me see. Okay, so fx plus 1 by fx, this is a positive quantity. Let me use this bound. 1 by fx is less than 3 minus fx. Okay, but I'll get from here upper bound. I need lower bound. So what I can say is fx, no, just a second, 1 by fx is less than 3 minus fx, and I know fx, this is 3, so this will imply fx is, yeah, correct. Okay, so see, so now from here what I can write is this term. So I'm just using this right hand bound. Okay, so I can write from here that 1 by fx is less than 3 minus fx, correct? And I know fx is positive. I know that fx is greater than 0, so minus of fx is less than 0. So now here I can say this is less than 3, correct? If my x is in 0 less than mod of x less than delta 1. And now from here what I can say is this f of x is greater, then I am getting lower bound. Sorry, I need upper bound. Okay, so no worries, I'll use the left hand bound then. Okay, so let me say in this way. So it's fine, I'll replace fx by, and then here I'll get 1 minus fx, this is less than 3, right? Again the same logic. So since this is positive quantity, this is positive, so this is negative, right? I mean with this minus sign, this is less than 0, so I'll get less than 3. So fx, I got that fx is bounded by 3, so that I can substitute here. But here what does it say? So let's say this is star. So star tells you that this inequality is true if my x lies between minus delta naught to delta naught, right? And this tells you that fx is bounded by 3 if my x is in minus delta 1 to delta 2 minus plus delta 1. So I'll choose, so let us choose delta, which is minimum of delta 1 and delta 2. Okay, if I choose, so let's say this is star dash. Okay, then star and star dash will hold for this. So choose delta to be like this, which is strictly positive. Now for
minimum of delta naught comma delta 1.
Oh, sorry, I've written delta 1. Sorry. Yeah. So it will be delta naught delta 1. So now for 0 less than mod of x less than delta, both of these inequality will be true. So what I can say is mod of fx minus 1 is less than, now this fx is bounded by 3, so I can replace here by it by 3 times epsilon, and now I can say that this is less than, okay, so maybe I can start with epsilon by 3. Okay, so let me say, I'll just adjust a bit. Okay, so maybe I can say epsilon square by 3. So this is 3, this is 3, epsilon square by 3. Okay, and what else? So I'll get here, this square is less than epsilon square, right? And this will prove, so this proves, and that is this mod of fx minus 1 is less than epsilon, and this proves the result, right? So this is what we wanted to prove. Yeah, is this clear? So again, this is something that we have been doing like since last class itself, right? So I chose some positive real number. I am using what I have been given. So I have been given that this limit exists and is equal to 2. So now I am just using the definition. Okay, and this adjustment is something that you can easily make. Okay, so this is not a very big thing to do. So we chose this epsilon square by 3, and then I got this quantity, and now I know that I got here fx, so I have to bound this. So for sufficiently small x, I can bound fx by 3. So now I'll choose delta to be minimum of these two, and then I'll get this kind of estimate which we wanted. Is this okay with everyone?
Yes, sir.
Okay. Okay, so now let's move to this question of continuity. Okay, so I hope you have already seen the definitions. Okay, so continuity is something which is related to the limit, right? So I'll just explain a bit, maybe just the usual definition, I mean not using epsilon delta. So suppose you have some function, okay, and you have some point x which is in the domain of function. Okay, d of f means I'm taking point, let's say it is c, which I'm taking from the domain. Then the question is, okay, so the first question is that limit extending to fx exists or not, exists or not. That is one question, right? This we have already understood that how to address this question, okay, whether this limit exists or not. Now the question comes up, okay, suppose this limit exists, okay, then the second question is, so this was the first question, the second question is, does this limit, okay, suppose that the limit exists. So if limit exists, so here the condition is if limit exists, then do we have this condition that limit value what we are getting is equal to the function value. So see, when we talk about limit, right, so you remember like we put this kind of condition, right, strictly greater than 0. That means we are not considering that point. So when we talk about this limit, this need not have, so this function, so here I have already mentioned that c belong to domain of a, but c need not, so c might not belong to the domain of f, right, when we talk about this limit. Okay, for this one we don't need that c may not belong to domain of a, we don't need this, right, when we talk about limit. We just need how it behaves near c. This is what limit means. But when you talk about continuity, you need to have this condition that, so maybe I should write a and b. So 2a and this is b. So the a condition is that C should belong to domain of F. That is, F of C makes sense or is defined, well defined. Okay, that means F at capital F at C should be sensible. Okay, so F of C is defined. This is the first condition. Now if it is defined, then the question is that does this limit what we are getting, is it equal to F, the function value at that point? If it is, then if this holds, then we say that the F is continuous. Oh sorry, so let me include all the three if you want that. So this limit should exist. Okay, so maybe I just put question mark over here. So if all these three holds, like if we get positive answer in all these three questions, then we say that F is continuous at C, right? This is the meaning of continuity. Okay, now using this fact, you can give epsilon delta definition, right? So which is similar to the earlier one. So the definition would be that for each epsilon greater than 0, there exists delta greater than 0 such that mod of fx minus, now we don't need L here, we know that L has to be equal to fc for continuity. This should be less than epsilon if my x minus c is less than delta, because if x is equal to c, then this is obviously equal to 0, so we don't need to remove that condition, like, so we don't need to put this kind of a condition here, right? That mod x minus c should be strictly greater than 0, this we don't need. Okay, because we know that the function is defined at c, so if I put x equal to c, it will be just 0. Okay, so that's what this continuity means. Okay, I hope you understood. Okay, so now let us go to solving these problems. So let's begin with the first question. So the first problem is f of x is equal to this box function of x, okay, where x is in 0, 2. Okay, so you already know how this function will, like, what will be the value of this. So it will be 0 if I take my x value from 0 to open 1, right? If it is strictly less than 1, then the functional value would be 0. It will be 1 if my x is belonging to this 1 comma open interval 2, and it will be 2 if my x is equal to 2, or x belong to singleton 2, right? This is the definition of the function. Now you can clearly see that the function is not continuous at 1 and at 2, right? If you look at as a graph, okay, so this is the graph, right? It's just 0 here, 1 here, and 2 here. Sorry, just 2. So this is my 1, and this is my 2, and this is 0, this is 1, this is 2, right? So this is the graph of function. You can clearly see that this, if you look at the limit, so the limit clearly does not exist here, right? So the first condition, it's, oh, I removed it, but the first condition itself is not true here. So clearly note that. So this is something I will leave for you, okay, but I'll hint you how to prove it. So note that limit x tending to 1, f of x does not exist. Okay, now since this does not exist, there is no question of whether it is equal to fc or not, right? So we don't bother about it. This does not exist, so f is not continuous at 1, right? Now the question is how to prove it. Okay, so you can clearly see, where should I write? I'll just hint it here maybe. So see, if I choose, so suppose that this limit exists, okay, then what will be the so suppose that limit x tending to 1, f of x is equal to L. So I am supposing it exists, okay, then I'll get a contradiction. How? So this would imply that for epsilon greater than 0, there exists delta greater than 0 such that mod of fx minus L is less than epsilon if mod x minus 1 is less than delta. right? This is the something that I'll get. Even so here it does not matter, because f at 1 we know it's defined, so I'm not putting 0 condition here. Okay, it's okay. So if you want, you can include 0. So maybe I should write, since we are talking just about limit, let me put this also. Now the thing is that if you see, so what does this mean? This, if x is belonging from 1 minus delta to 1, okay, so I'm taking the left interval, okay, in the left hand side, then you can clearly see that mod of fx minus L would be equal to mod of L, right? And if you choose x from 1 comma 1 plus delta, okay, this mod of fx minus L would be mod of 1 minus L, correct? Now the question is that from here you have to get a contradiction, right? Now suppose I choose my epsilon. So what should I choose? Maybe just a second. So 1 minus L. So this will tell me, okay, let me see what epsilon I need to. So suppose this is less than epsilon, this is less than epsilon. By this condition I'll get this. So this tells you from here that L will be from minus epsilon to epsilon, and this condition tells you that 1 minus L will be from epsilon to minus epsilon, and this will imply that L is from so let me first multiply by minus, and I'll get epsilon greater than L minus 1 greater than minus epsilon. Now I'll add 1. See, if I add 1, I'll get 1 plus epsilon, so it is 1 minus epsilon less than L less than 1 plus epsilon, right? This is what I'll get. So this is from, let's say 1 is giving me this condition and 2 is giving me this condition, right? Now you can clearly see that if I choose my epsilon to be half, okay, or 1 by 4, okay, so now I'll choose my epsilon. So for epsilon equal to 1 by 4, let's say. Okay, so this condition tells you that L will belong from minus 1 by 4 to 1 by 4, and this condition tells you that L will belong from, so this will give you 3 by 4, and L is from 5 by 4, which is clearly contradicting, right? This is telling you it is less than 1 by 4, and this is telling you that it is greater than 1 by 4. That is a contradiction. So this proves that this limit will not exist. Okay, so this is something we have talked earlier also, but anyway I already wrote the solution. But this is how you can prove that the limit does not exist. Okay, but at other points if you look, okay, so maybe I'll just say, so from here I'm getting here. Okay, so similarly what you can prove is, similarly you can argue, we can say, or we can show limit x tending to 2 f of x does not exist. Okay, and this proves you, and this tells you that f is not continuous at 2. But if you choose any point, so maybe this was 1 point, this is the second. Now suppose let c belong to 0 to minus 1 comma 2. So you remove these 2 points, then you can prove, then my claim is that f is continuous at c. And you can clearly see, right, because my function is constant over there. So if I choose any point, so suppose I choose this point, okay, then in this neighborhood this function is constant. So if I do, so if I evaluate here fx minus fc, then I am getting 0, right, because the function is constant, correct? So this will tell me that for each c which is not equal to 1 and not equal to 2, I'll get constant. This difference is going to be 0. So maybe I'll just write one line, then for sufficiently small delta, okay, I'm writing it roughly but you can understand. So why I'm writing this sufficiently small? So that this point does not cross 1, okay, That's why. So for sufficiently small delta greater than 0, f of x minus f of c is equal to 0 if this x minus c is less than delta, that is x belong to c minus delta to c plus delta. Right, these are the same thing. Okay. Okay,
Sir,
so
I have a doubt. Sir.
yeah, sure.
Sir, you have said that it is a constant function where we belong to closed interval 0, 2 minus 1, 2. But there is a jump. It takes two values in from
No,
0 to 1 open. Yeah.
I'm saying it is constant in this neighborhood, right? In this neighborhood, if you see, it is constant 0. So if I choose this point, okay, any point in this interval, then in this neighborhood it is constant.
Oh.
And for continuity, you just have to look in a neighborhood, right? So now when I look at the neighborhood, I can see that this is a constant function. So the value of fx here and the value of fc is going to be the same, right? And so the difference is going to be 0. Correct? In the neighborhood, I'm saying.
Thank you, sir. Okay.
You got the point?
Yes, sir.
Yeah, so that's why we have this, that difference is going to be 0, and this is obviously less than epsilon, right? Whatever epsilon you choose, it does not make any difference. Okay, so we have, so this tells you, so f is continuous at c, which is belonging to 0 to minus, so maybe I have already written that where my c is, so it is continuous at c. Okay, so it is discontinuous only where there is a jump. In the same way we can deal with other problems, so maybe I'll just, you can clearly see this, I'll just write what the function is explicitly. Okay, so the second function is x minus box x, and the third function is x times box x. Okay, so this is also called signum function, as far as I remember. Okay, let me not mention it, but it has a name. Okay, so here again x belong to 0, 2. Okay, so let's see how this function looks. So suppose, so
Sir,
why, yeah,
for option A, the answer is f is not continuous.
yeah. So I have written it vaguely that what, check the continuity. So when I say you check the continuity, means like at what point it is continuous and what point it is discontinuous, because continuity is something which is pointwise property, right? You say the you never say that f is discontinuous just directly, you mention. So okay, so let me say, so suppose this is I cannot say f is continuous. When I say, I have to mention it is continuous on the domain, like, so let's say when it is continuous on the whole domain, we just say that the function f is continuous, right? But suppose a function, so what should I say is basically, okay, I should say in this manner that the property of continuity is something pointwise. It's like whenever you define continuity, you say f is continuous at c. You never say f is continuous on the interval. When you say f is continuous on interval, that means it is continuous at each of the point, right? So continuity is something which is pointwise property. This is the first thing. The second thing is, so when you want to, so in this question I just mentioned that check the continuity. That means that you have to check at what point it is continuous and at what point it is not continuous. Okay, so this is what I mean. But okay, if you want to conclude from here, you can say that f is not continuous in 0t. So from here the answer you can write is like this: f is continuous on 0 t 2 minus 1 comma 2, and f is okay, so when I write it discontinuous at x equal to 1 and x equal to 2, like this, you can maybe, this would be a better answer Although what you said is also correct, that you can say that f is not continuous on 0, 2. Okay, but this is something which is more precisely you can say where it is continuous and where it is failing discontinuity. Okay, so now let's go to the second problem. So we have this example, correct? So now here again I'll break my interval in 3 parts. So I'll first consider 0, 1. The second would be 1, 2, and the third would be x equal to 2. Okay, so maybe I'll just shift it up. Okay, so let us see what the function. So in 0, 1 I know that the box function is going to be 0. So this fx is just x, right? In 1, 2 I know this box function is 1. So in this case it will be x minus 1. In x equal to 2 I know that this function is going to be 2 and 2, which is 0, correct? So this is my function. So if you want to plot the graph, okay, just a second. Yeah, okay. So now if you want to plot the graph, you can plot it in this way. You can see. Okay, so we have this 0 and then 1, let's say, and then this is 2. So in 0, 1 you have that this is just this x. Okay, it is hollow over here. Now at 1 you can see it is 0. So at 1 you have here, and again it is x minus 1, that means it is straight line which is like this. Okay, and at 2 it's again 0. So this is how this function looks, and you can actually define this function on whole of R, okay, or whole of positive real number. It would be like this. Okay, it will go on further. Okay, so over here we have this. Now again here you can clearly see that it is continuous at 1 and 2. Okay, so now I will not do it, maybe you can check. So f is continuous at x continuous on 0, 2 minus 1, 2, and f is discontinuous at x equal to 1 and x equals to 2. Okay, okay, you can also write it in terms of left hand limit, right hand limit, right? So maybe I can give this solution as well. So you can see that limit x going to 1 plus f of x, right? So when you are coming from right, you are getting x minus 1, which is 0, right? And when you go from left hand side, 1 minus f of x, you can see that this is going to 1, right? So it is 1. So limit x tending to 1, f of x does not exist, because left hand limit and right hand limit are different. This is my RHL, this is my LHL. Okay, so this is another way. Like the first problem I solved using epsilon delta definition, and now this one I am giving another way, like you can write this solution in this way as well. Okay, okay, now let's move to this third problem. So let's see what comes up here. So when my x is in 0, 1, when x is in 1, 2, and when x is equal to 2. So when x is in 0, 1, I know this box function is 0, so therefore I'll get 0. When this x is in 1, 2, I know this box function is going to be 1, so this will be x, and when x is equal to 2, I'll get 4, right? So now again, if you want, you can plot the graph. So this is 0, this is, let's say, 1, this is, sorry, this is, let's say, 2. Then in 0, 1 the value is 0, so at 1 it's hollow. At 1 the value is 1 because it's x, so maybe it should be here, and then you go a straight line like this till 2. So this is my 2. Okay, so this is 1, this is 2, and then at 2 you have the value 4. Maybe let me draw, this is 3, this is 4, so at 2 you have the value 4. So again you can check that f is discontinuous at 1 and at 2. Okay, so again the same thing will happen here as well. Okay, is this clear? Okay. Okay, so now let's proceed to the next problem. So you have been given this function, okay, which is defined in this way. So f of x is going to be 1 minus cos ax b upon bx when x is non-zero, and at x equal to 0 this function is clearly not defined, right? So you see, if I just look at this function, then it is not defined at x equal to 0, because if you put x equal to 0 you will get 0 by 0 form, right? So but limit will make sense, but this, if I put just x equal to 0, it does not give any meaningful real number, right? 0 by 0 is not a meaningful real number, but we know if it's in 0 by 0 form, we can talk about limit. Okay, we can see if the limit exists or not. Okay, but so since we are talking about continuity, we are intentionally defining my fx as c. Now the question is, what should be the value of c so that this function becomes continuous? Okay, so the question is, what is this my c so that the function will become continuous? Okay, so what does continuity means? So the first thing is that this limit x going to 0 f of x should exist. Okay, this is the first condition for continuity. The second condition is that limit x going to 0 f of x should be equal to f of 0. Now what is f of 0 here? It is c. Okay, so if you want this function to be continuous, first you have to show that this limit should exist. If this limit does not exist, then we are done. Then we can say that for whatever c you choose, it is going to be discontinuous, right? But if when this limit exists, you have to choose c as the limit value, right? Then the function will be continuous. Did you understand what I'm trying to say? Yeah. Okay, so now let us see that whether this limit exists or not. So the first thing is to check that this limit exists. Okay, so maybe, so the function, let me write the function again. It is 1 minus cos of x upon bx when x is non-zero, and it is equal to c when x is equal to 0. So first I'll check that. So limit x going to 0 f of x, so I'll have to find is equal to what. So this is my first goal. Okay, okay, so now I mean, you can show it in a different way, like what will be the limit, but I'll use the maybe the easiest thing, that L'Hopital we all know. So I'll just use directly that to get, or maybe I can just simplify it further as well. So maybe let's not use L'Hopital. So has sir introduced L'Hopital rule in the class? I just want to know this. Has he talked about this? No idea.
I have not watched the videos, sir, but I know the hospital rules.
No, you know is fine, but I don't know if you are going to give exam and if sir has not talked about it in the class, then I don't know whether you will be given marks for that question or not. So that's why I was concerned. But anyway, so let's not go with L'Hopital. So we'll try to do it directly. So f of x, okay, so this is nothing but limit x going to 0. So for x going to 0, that means x is not 0 when I talk about limit. So I can say my fx is this one, right? So I'll just write 1 minus cos of ax upon bx. Okay, so let's simplify it further. So limit x going to 0. So 1 minus cos ax, I know it's 2 sine square. So 1 minus cos theta is 2 sine square theta by 2. So here I'll get ax by 2, and then I have bx. Okay, so again this does not make sense. So what now I'll do, limit x going to 0. So I'll put sine square. So let me take 2 outside, maybe 2, and okay, let me take 2 outside. Okay, let's see. So limit x going to 0, sine square ax by 2. Okay, and then here I'll divide ax by 2, then I'll multiply ax by 2 since I've divided it, and then I'll have 1 by bx, right? This is what I have. Okay, now I know, so this is something that I have already proved, that limit x going to 0 sine x, let me write in terms of y, sine y by y is equal to 1. This is something that I have already proved. Okay, so I'll use that one. So what I can do is, now I know that this limit okay, so I should put here square maybe. So let me put square. Okay, so now you can see that this limit exists and this limit exists. So this limit is going to be 0, right? Because if I cancel x with this one, so I'll get this. So maybe I can write this. So check. Okay, so maybe how should I write? Okay, I'll write it in bracket. So limit x going to 0 sine square ax by 2 upon ax by 2 whole square is nothing but, so now I am writing this as y. Okay, so new variable. Now okay, so now I am writing it as limit. Now as x goes to 0, y will also go to 0 because y is equal to ax by 2. So this is limit sine square y upon y. This is nothing but limit y going to 0 sine y upon y whole square, right? By product rule of limit. So we have this, and this is 1, so this is 1 square. Okay, now the second, okay, so
Sir, here you have taken the value of y to be ax by 2 the whole square.
correct.
But in
no,
sine square,
sorry. This is y square. Okay, this was the doubt, no?
Yeah, yes, sir.
Yeah, so yeah, now it's correct. Okay,
Yes, sir.
yeah, I missed it somehow. Okay, so this is one thing. The second thing what I wanted to say, so okay, in continuation of this, so limit x going to 0 ax by 2 whole square times 1 by bx I am saying. So this, if you see, this is nothing but limit x going to 0, this is a square by 4b and then you have x, right? So this is nothing but 0. So you know that the limit of this exists, limit of this exists, so the limit of product will also exist, and the value will be the product of the limits. So this is nothing but 2 into 1 into 0, which is eventually 0, right? So what we have obtained is that the limit of this function as x goes to 0 is equal to 0. Okay, so let me write, so limit x going to 0 f of x is equal to 0. So, and hence for f to be continuous at c equal to 0, okay, we must have f of 0 equal to, okay, maybe I should write x naught. Okay, so f of 0 is equal to limit x going to 0 f of x, and this is 0, so this implies that c, it has to be 0, right? So this is the answer, that if we put c equal to 0, then the function will be continuous at 0. If I put some c which is non-zero, then the function will be discontinuous at x equal to 0. Okay, is this clear? Okay, so now let's proceed to the next. So maybe should I leave this one, because I have more other important question to discuss. So if you have confidence that I'll be able to do this, then I'll leave, otherwise I'll do it. So what do you want?
Yes, sir. In Saturday class, the sir did this problem, sir.
Oh, this was already done?
Yes, sir.
Okay, so maybe I'll just leave it as exercise. Okay, fine. Okay, so now let's come to this problem. So over here you have to give an example of a function which is discontinuous at exactly one point. Okay, now I'll ask you for giving some example. You have already seen many examples, hopefully. Can you give me some example which is continuous everywhere but it is discontinuous at one point? It is very easy, right? Can you give me?
In the previous example, you have taken 0 to 2 instead of that 0 to 1.
Correct, right? If I just restrict to 0 to 1, then we are done.
There will be a 1 breakpoint 1.
Correct. So I am writing fx equal to x, which is equal to 0 if x belong to 0 comma 1, and 1 for x equal to 1. Then it is discontinuous at just one point. So f is discontinuous at x equal to 1 only, right? Okay, now give me some example which is discontinuous in the, give an example of f which is discontinuous in the whole domain. So it is not continuous anywhere.
Rational points and irrational points.
Correct. So can you tell me what should be the function if x equal to
0 if x is rational and 1 if x is irrational.
1 if x is this discontinuous, do you think? Okay, 1 you are taking, yeah, then it's discontinuous, right? Because there is jump, continuous jump. But what if I put x here? Okay, just I'm asking, what if I put x here? Then what will be the like, how will the continuity be affected here? Can you tell me?
It will be continuous at the irrational points.
Is it? Okay, tell me, limit x tending to c f of x exist. Is it true for c belonging to 0, 1? What do you think? What will happen for c equal to 0?
The limit exists
For everywhere?
for c equal to 0, sir.
What about c when c is non-zero?
The limit does not exist, sir.
How will you argue that?
Between any two rational points, there is a irrational.
Correct. Yeah, I think you understood. Okay, but I will tell you. So this is another example. So okay, so let me write what you have just said. So if I take x equal to 0, f of x, this limit exists and the limit value will be 0, right? Because if you see that whatever sequence you take, whether rational, irrational, like this x is also going to 0 as x is tending to 0. Okay, so this mod of fx minus 0, if you see, this is going to be, I think this was discussed. I think I have discussed this problem. So this will be actually equal to mod of x if x belong to r minus q intersection 0, 1. Okay, and it is 0 if x belong to q intersection 0, 1, right? And this will tell you that this is going to be less than epsilon if I choose x to be sufficiently small. Okay, so this I think I have already discussed, so there is no point of discussing this. Now you already know that f is equal to 0 at x equal to 0, right? Here you see. Okay, so this is equal to f of 0. So this means this tells you that f is continuous at x equal to 0. Okay, maybe like, is this for the third? Okay, maybe this will serve for the third example. Okay, so maybe this is C, I think. Yeah. Okay, so f is continuous at x equal to 0. Now if you look for any other point C, then you see this does not exist, and the reason is very simple. Like you see, if you take any C point, okay, C belong to 0, 1, then there exists a sequence xn of rationals and yn of irrational. So suppose xn you get, which is in r minus q intersection 0, 1, and yn you get in q intersection 0, 1. Okay, which are converging to C, such that xn comma yn will converge to 0, sorry, C. Now if you see f of xn, okay, f of xn is going to be what? It's irrational, so f of xn is nothing but xn, and this will going to C. But f of yn, you see, f of yn is 0, right? So this is a constant sequence, so it is going to 0. Now you know that C is not equal to 0, so this is a contradiction, right? So you got two sequences which are converging to two different limit points. I mean, the sequence is converging to the same point C, but their functional values are converging to two different points, and this proves that this function is not continuous, right? This is the sequential criteria, that if you can obtain two sequences which are converging to the same point but their functional value are converging to two different points, then you can say that f is discontinuous, right? Okay, so this proves that this limit does not exist actually. Okay, so this proves that the limit does not exist. Now since the limit does not exist, you cannot talk about the continuity. Okay, so this was the third. For C part, this would be an example, so I'll just cut this off. Okay, now let's come to B. I think you already mentioned the example. So fx equal to 0 if x belong to, let's say, Q intersection 0 1, and 1 if x belong to R minus Q intersection 0 1. So let me put it. So f is discontinuous everywhere, and the reason is again the same, right? You can take two sequences. So maybe I'll just copy this answer here. So reason is same, x and y n. So let's say C belong to 0 comma 1. So f of xn, this is going to be equal to xn comma yn converge to C. F of xn is going to be 1, f of yn is going to be 0. So this converges to 1, this converges to 0. So this proves that f is discontinuous. Okay. Okay, now again, like here you can see, like if I switch the value, if I put x here and if I put 0, okay, then also it's continuous. No issue. So it's the same thing. Okay, so this was about this. Here you have to give some examples. Okay, so I hope everyone understood this. Is this clear to you? Okay, so now let's move to the next problem. Okay, so now here you have been given this function, and then you have to find the points of continuity for this function. Okay, so for continuity, again I am writing two conditions. So I will just write C belonging to 0 2 is point of continuity for f if the first condition is the limit x going to C f of x exist, and the second condition is that limit x going to C f of x is equal to f of C, right? So you have to check these two conditions. Okay, so let's talk about first that existence of limit maybe. Okay, okay, now how should I say this? Maybe like what you can think is, should I write in terms of left hand limit and right hand limit? I think that is the best possible what I can do here. Okay, so let me write it in this way. So let C belong to 0 2. Okay, then limit okay, so see, I'm just trying to guess. Okay, so how to guess is like when you have, so let's say you have two sequences, one in rational and one in irrational. Okay, so maybe I'll prove like what is the discontinuous point or where the limit does not exist. Okay, so suppose you have two sequences xn and yn. Okay, so xn and yn both are converging to C. Now if you look at f of xn, this is 2 of sorry, so okay, let's say xn is rational or irrational. Let's say it's in r minus q or q complement. It's in q complement. Okay, so f of xn, since xn is rational, so it's going to be x square xn square, and this will converging to c square because xn is converging to c, so xn square will converge to c square. If you look at f of yn, you will get yn 2yn, that means it is converging to 2c, right? So maybe I should write here why I'm writing here. So I'll tell you one main thing here. So now then by density there exists sequences xn in q intersection 0 2 and yn in q complement intersection 0 2 such that this xn comma yn converge to C. Okay, both the sequences are converging to C. Now f of xn, okay, since x is in q, so this is xn square converges to C square. F of yn, which is 2 of yn, this will converge to 2c. Okay, for limit to exist, at x equal to c, we must have 2c square equal to 2c. If you evaluate here, you will get c times c minus 2 equal to 0. This will give you c equal to 0, c equal to 2. Okay, so if I choose my c from the open interval, okay, then this gives a contradiction, right? Or I mean, this proves that but c belong to 0 2, therefore limit x going to c, f of x does not exist, right? So this is what we can prove. So using this, so see, this is what I wanted to mention. So suppose you want to prove that it is discontinuous at some point C, then what you do, if you can bring two sequences which are converging to C but their functional value is converging to two different points, then you are done. But to prove that f is continuous here, you cannot just use two sequences and so for example, here you cannot say that it is continuous at c equal to 0 and at c equal to 2 just using this argument. Okay, that is not true. So maybe I should tell this. So when I say limit extending to c f of x exists, this means that this is a definition. If for all sequences xn converging to C, f of xn should converge to same limit. Converge to same limit, right? Same limit L. Okay, so maybe I should write this is equal to L if this happens. Now here you have to see that this is for all sequences, but here we are choosing two particular kind of sequences, xn and yn, where one is the sequences of rational and the other is sequence of irrational. So these are two particular choices that we are making over here, right? So from here we cannot conclude that c equal to 0 or c equal to 2 is the continuity point, but what we can say is that if c is not 0 and if c is not 2, then obviously this is point of discontinuity. Okay, so this kind of argument is always going to help to prove whether the function is discontinuous at some point or not. For proving continuity, you cannot use this kind of argument. Okay, that's all what I wanted to say here. Okay, so now let me, so what we have got is that it is discontinuous at c not equal to 0, c in open 0 2. Okay, that we have already proved. Now the question is, so this is done. Now the question is the function continuous at c equal to 0? Okay, So okay, so for c equal to 0, let us see. Okay, so what is although you can clearly understand that both x square and 2x both are going to 0, so the function is going to be continuous, but the point is how to prove it, right? That's the main thing, like how we can prove. So we'll prove it the same way, like how, using this epsilon delta definition. So c equal to 0, so 0 is a rational point, so f of c is going to be 0, right? So c equal to 0, so this would tell you that f of c is going to be f of 0, which is equal to 0 square, which is 0. Okay, nice. So we have to estimate f of x minus f of 0, and f of 0 is 0. So this thing what we have to estimate, right? Now this is nothing but, if you see what is f of x, so either it's x square or 2x. So now this I'll write it as, it is mod of x square if x belong to q intersection 0 1, and it is 2 mod x if x belong to q complement intersection 0 1. Okay, this is what we have here. Okay, so now what we have to do is we have to show that this is going to be less than epsilon. Okay, so maybe I should have written here that let epsilon greater than 0. Sorry. So let epsilon greater than 0 be any real number. Okay, okay, so now you have this, the functional value is like this. Now here you see this is, you can clearly make this less than epsilon if my x, so I am talking just about the first case, if mod x is less than root epsilon, right, for the first one, and x is belonging to q intersection 0 1, right? This is the condition what we already have. This is less than epsilon if my mod x is less than epsilon by 2, and x is belonging to r minus q intersection 0 1. Okay, so now what you do, you just take delta, which is minimum of these two. Okay, so define, so choose delta which is equal to minimum of root epsilon and epsilon by 2, right? Then what do we have? Then this mod of fx minus 0 is less than epsilon if 0 is less than mod, or if mod of x minus 0, or if mod of x is less than delta. If you want, you can include. Yes, so this proves, this implies f is continuous at x equal to 0. Is this clear? Similarly, you can prove for x equal to 1, right? So I'm not going to prove it, but so you can see maybe. Okay, so again, if I'll just tell you briefly. So you see that f at 2, if you see that this is going to be 2 square, so I mean this is going to be 4, right, f of 2. Now here if you see, this x square is also going to 2 square, so I'm just saying you roughly, and this 2x is also going to 2 into 2, I mean both are going to the same point, so therefore it will be continuous, that you can see. Now the only thing what you need to do is you have to prove it precisely using this epsilon delta definition. So do you want me to do this, or will you be able to do it directly, like by one? What do you want?
We will do it, sir.
You can do it? Okay, then I'm not discussing
Yeah,
it.
yes, sir.
But similarly
But
you can
I
do.
have a doubt. You have written.
Sorry?
We have written in all the places q intersection 0, 1 in the proof. Whether it is closed interval 0, 1
Oh,
or
sorry,
it is
no,
closed
no.
interval 0, 1.
Sorry. It is 2. Thanks for saying. Everywhere it's 0, 2. Now for the second case, like I'll just say that this fx minus f2 is nothing but fx minus 4, and if you see, this is either x square minus 4 or it is 2x minus 4, right? Now here you can see it is x plus 2 and x minus 2, and here we get 2 times x minus 2. Now this is clearly less than epsilon if x minus 2 is less than epsilon by 2, and this will be, you have to again use the same thing, you just bound this thing by some c. Okay, you choose delta which is 1, let's say, then for x minus 2 less than delta you will get that this is bounded. Now you will define delta to be minimum of this 1, and here you will get epsilon by c, whatever c you get, and then this epsilon by 2. Okay, so now using this you can say that for this delta my definition would be satisfied. Okay, it's the usual thing what we do. It's just that we have two things over here, so we have to make both of them less than epsilon. So this you already know how to do, this you already know how to do. Now just take delta to be minimum of this and one thing, one more quantity which is 1. Okay, then you are done. Okay, so I'm not writing it precisely, but you can do it similarly. I'll just write one line. Similarly, one can prove, one can show that f is continuous at x equal to 2. Okay, fine. Now let's go to the next problem. Okay, so here again similar kind of thing what we have seen earlier. So this is the function that has been given to you. This is a rational function. So you have to check. Okay, so you have to find the value of k for which this function is not continuous at x equal to 3. Okay, so you know this thing that polynomial is always continuous, right? You know this. Yeah. You know this, no? Like if the polynomial are continuous. No? Okay, so maybe I'll just say it, but it's very trivial. Like you know this x is continuous. So x times x, if you do, the x square is continuous. Then again you multiply by x, then x cube is continuous. Then you can say x raised to the power k is continuous for all k. Now if you multiply by alpha, then this is also continuous, right? So in this way you can say that polynomial or continuous function. Okay. Now p is, let's say p is a polynomial, then I know p is continuous. Okay, polynomial I'm saying. So let's say they are p1 and p2 are two polynomial, both are continuous. Then you can say that p1 by p2 is continuous if p2 x is non-zero for all x belonging to the domain. Okay, so maybe the domain where I'm considering these polynomials. Okay, so when we are talking about polynomial, it basically means that it is R, because polynomial is defined in the whole R. So if it is not equal to R, if x for all x belonging to R, if this is non-zero, then you can say that p1 by p2 is continuous. Right? This you must have seen. I mean, this thing you must have seen, that f continuous at C, G continuous at C, and if G at C is non-zero, then f by G is continuous at C. Right? This you must have seen, this result. So I'm using the same result to tell you that this is true. Okay, this is a particular case where I'm taking p1 and p2 to be polynomial. Okay, so now this is continuous. So this is continuous if my numerator or denominator is non-zero, then we know that this is continuous. Even when it is 0, okay, then you cannot make sense, obviously, right? Because suppose if this quantity is equal to 0, okay, then, and even if it is also 0, then f at that point C will not make sense, right? Will not make sense. This limit, this might make sense. Okay, so this might be sensible, right? But so for example, let me, so what example should I give? Okay, leave it. So I'm not giving example, but what I'm saying is uh, that this might not be sensible to define that at C, if you can precisely give the value that okay, f at 0 is so for example in this case you can say that f at 3 I am defining its certain value, then you can say that it is continuous, but in general you cannot say. Okay, so now let me come to the solution. Clear. Okay, so now let me come to the solution. So over here we have, so it was just few remarks what I just wanted to tell. Now let's come to the solution. So over here you see this f of x is equal to x square plus x minus 6 upon x square, sorry, plus kx minus 3. Okay, now the numerator can be factorized as, you can see minus 6, 2 into 3 you just break, so what you get is x plus 3 and x minus 2. So this is x square plus kx minus 3. Okay, now what I can do is, so so basically what we have to do is we have to find the value of k, okay, so that this is not continuous, right? So if I find the value of k for which, okay, so let me just say what is the limit, then maybe I'll come to that. So let's say I want to evaluate limit extending to 3, right? So I want to talk about this point. So what will be the limit? Okay, so you just substitute 3. Okay, let's just substitute 3, then what I get is it will be 3 plus 3 is 6 times 1 upon 9 plus 3k minus 3, right? So this is, so I don't even need this factorization. Okay, so let's forget about this. So what you have here is 6 upon 3, you can take common, k minus 2, right? So here you will get 6, just a second, it will be plus, right? So this is what you get, okay, the limit value. I mean this is your f of 3, maybe I should write, let's say f of 3, let's not write limit. So f of 3 is this, okay, this is the function at 3. Okay, that would be the best way to write. Let's not talk about limit at this point. So now for f to be discontinuous, for f to be continuous, like here what do you want, it's not continuous. So if I take k, which is, so if I take k belonging to, if I take k equal to 2 minus 2, then f of 3 is not defined, right? And you can look at this also. So let me put here 2. Okay, so maybe I should write, okay, let me write it this way. So from here you are getting that if I take k equal to minus 2, then it will be a problem. So let's say, so case 1 maybe, or just take k is equal to minus 2. Okay, then let's see what is f of x. So f of x is x plus 3 and then you have x minus 2. So I'll tell you why I'm writing all this, because see, it might be the case here that in this denominator you can have this kind of factor, x minus 2 or x minus 3, let's say. Okay, okay, but over here it's not make sense. So suppose, let me give another example. So suppose you have something like this, x minus 3 and x minus 2, and then here you have x square plus kx plus minus 3, let's say. Okay, now you want to evaluate at x equal to 3, correct? So this is giving you 0, right? So if you can factorize here, let's say if I'm getting like this, x plus bx, let's say, then you can clearly see this x minus 3 will cancel out, and then you will have a finite limit. I mean, if you just substitute x equal to 3, then you will get finite limit. So the limit might exist, okay, but over here you see there is no factor as such in the numerator. There is no x minus 3 because here you are taking x equal to 3. So if in the above there was x, if there was a possibility that the limit will exist, then in the numerator it should have x minus 3 as the factor. Then only you will get 0 by 0 form, and then everything will work. Because here you see, if you just substitute if x equal to 3, you are getting something finite here, right? Okay, so if I take k equal to minus 2, then this limit will not exist. Okay, everything will not exist. So this limit, this is also not true. X going to 3 does not exist, and hence f cannot be continuous. Continuous at x equal to 3. Okay, but if you take k not equal to minus 2, okay, then what I was saying earlier, that my x square plus x minus 6 is continuous on R, x square plus kx minus 3 is continuous on R. So let me say this is fx, this is gx, and g at 3, okay, because we have to deal with continuity at here. G at 3 is x square plus kx minus 3, sorry, why I am writing this, is equal to 3 into k plus 2, right? This is what we have evaluated here, and this is not 0, right, on R, since k is not equal to minus 2. Okay, so this proves, therefore fx by gx is continuous on R. So if k is not equal to minus 2, then I have that the ratio is continuous on whole real line. If k is equal to minus 2, then this limit will not exist, and hence the function is not going to be continuous at 3. Okay, is this clear, or did I mess it up? I don't know. Maybe you can ask if you have some doubts. Is everything okay here? Okay, then let's quickly move to the next problem. So this is the next. So here we have this function fx given as cos 1 by x when x is non-zero, and at 0 you can clearly see that at x equal to 0 you cannot make sense of this, right? So you define at 0 as 0. Now the question is to prove that whether this function is continuous or discontinuous. So over here it's given that you have to prove that f is discontinuous at 0. Okay, so basically what you have to prove is that either you show, so here you already know that f of 0 is given, so you have to show maybe, so there were two conditions, right? Limit x going to 0, f of x should exist. Okay, this is the first condition. The second condition is that limit x tending to 0, f of x is equal to f0. Now here you have been asked that prove that f is discontinuous at x equal to 0. That means either you have to show that this will not exist, and if it exists, then you have to show that this cannot be equal to f of 0, right? So let us see which condition is going to fail over here. Okay, so the solution maybe, so let's say limit, so you see this is your function, maybe I should write first function. This is cos 1 by x when x is non-zero, and 0 if x is 0. Can you just tell me, I think I already discussed this kind of problem earlier, can you tell me that the limit will exist at 0 or not? I think one of you only answered this problem, right? I think that you took two sequences. Do you remember? Like I think it was sine 1 by x, but the same argument would work here. Can you recall? No. So let's say you choose this sequence xn as, let's say, 1 by 2n pi. Okay, this is going to 0. Now you choose another sequence yn as let's say 2n plus 1 pi, odd multiples of pi. Now again this is going to 0. Now if you look at f of xn, okay, this is equal to 1, and if you look at f of yn, that will be minus 1. Correct. So this clearly, this f of xn, this, so the limit n going to infinity, just limit f of xn is not equal to limit f of yn, but both xn and yr both are converging to 0, right? So this proves, this shows that limit x going to 0, f of x does not exist, right? Now since this does not exist, it cannot be continuous, right? So this, the first condition itself is not true over here. Okay. Okay, so or maybe like, so what I mean to say, so suppose here if I put x, okay, then the limit value, you can check that the limit will be equal to 0, and if I suppose if I put here 1 in the definition, then in that case the second condition will be false. Okay, so both can happen. Okay, so this was just a remark. Okay, now let's move to this next problem. Okay, so this is quite maybe different from the earlier one, because earlier what we were just looking at this continuity of some given function. Now we have something abstract, right? So we have just one property. So you have been given this f, okay, you have been given that it is continuous at 0, and it has this property, f of x is equal to f of x square. So you have to prove that this function is continuous. Okay, so there are only two things that has been given to you. The first thing is that f is continuous at 0. The second thing is that f of x is equal to f of x square. So you have to prove that it is constant function. Okay, can you tell me like what can we do? Do you have any idea like how can we prove it? So basically what you have to show, so from here you can see one thing, that if I put x equal to 0, I'll get f of 0 equal to f of 0, this which will tell me that f of 0 is equal to 0, right? So one value is known to you, f of 0. Okay, so let's leave the 0 point. Now the question would be like, can I say, so what we have to prove, that it is constant. Okay, so what we have is, so what I was saying, that f of 0 is some sense it's known to you. Now goal would be, and you also have this property, see, that it is continuous at 0. So using this something, what you have to show, that f of x, okay, is going to be f of 0, okay, for all x. So this is something, if you can show that it is equal, that at all the values, okay, for x in minus 1 1, the functional value is equal to the function value at 0. Okay, so this is the hint, like this is how you can think. Okay, because it would be very difficult to show fx is equal to fy for all xy in minus 1 comma 1. I don't know if you can prove this, but what you can definitely show, like you can deal with this fashion, and you have to use this property. So two things you have to use, continuity at 0 and this property. Okay, the solution is quite interesting. We will just start solving now. So see, what you have been given is that, so so I have to prove this thing, right? So I will choose let x belong to minus 1 comma 1. Okay, what I have is, then you see what you have, then it says that f of x is equal to f of x square, right? And this property is also important, that your x is just lying between -1 and 1. So if I replace this condition, x belong to R, then I don't think that it should be true, that it's constant function. I don't think. Okay, so let's see. So you have f of x is equal to f of x square. Okay, so what does this mean? This basically means that f of x times x, right? So let me write this. So f of x is equal to f of x times x, or f of x square. Now again you can apply the same rule here, right? So f of x square, again you can write that f of x square is equal to f of x square times x square, right? So this is equal to f of x4, right? Again what you can say that f of x4 is going to be equal to f of x raised to the power 8. Are you getting? In this way what you can say is f of x is equal to f of x. So what will be the condition? So let me see. So f of x square, so you are just how should be the general term be written? Just a second. So x of 8 times 8, f of x, f of x1 plus 1. Okay, so this is the first iterate, kind of. This is the second iterate. So the nth iterate can be written as f of x raised to the power n, x raised to the power n, so till n times, right? I hope I'm writing right. So no, I'm not writing it correctly. This is x4, no, this is not true. Just a second. So what I can say is, okay, let me write it in this fashion. Okay, so now let me write in this way. Maybe f of x is equal to f of x square. This is equal to f of x square square. Okay, this will help. F of x square square. Okay, this is equal to f of x square square whole square, right? In this way you can go, and ultimately what you get is x square. So at each level you are multiplying by, I mean, itself, right? So it is, you are taking square every time. So it is 2 plus 2 plus 2 plus 2, 2, like this will be n times, right? Is this correct? No, sorry, why I'm doing plus, it would be into, right? It will be multiplication, because this is nothing but, you see, this is x 2 times 2, this is x 2 times 2 times 2, right? That's why. So you will get this. So this is nothing but f of x raised to the power 2 raised to the power n, right? Okay, so what you have got is f at x is equal to f at x raised to the power 2n for all n, right? Now you notice this thing, this quantity. So let me define this xn. I'm defining it as x raised to the power 2 raised to the power n. Okay, now you can clearly see that since mod of x is less than 1, so xn will go to 0 as n goes to infinity, right? This you can understand, right? This is nothing. Is this clear? Like xn will go to 0, because this is nothing but 2 raised to the power n. As n goes to infinity, 2 raised to the power n goes to infinity, and you know that this goes to 0 as n goes to infinity. So you can replace 2n by m also, like so you can prove it. It's not a big deal. So just using this kind of thing, you can, the proof will be similar. So x raised to the power 2n will go to 0 as n goes to infinity, because this 2 raised to the power n is going to infinity. Okay, so some same logic will be true here. Okay. Okay, and you also know that this function is continuous at 0. So this will imply that f of xn will converge to f of 0. Since f is continuous at x equal to 0, right? This is done. So, and so this f of 0, what is f of 0? F of 0, I have already said that it is 0. Anyway, you don't even need that, the value. But over here we know that f of 0
But
is...
how did you tell, sir, f of 0 is equal to 0? Just simply writing f of 0 equal to f of 0.
Yeah.
We have written.
Oh, sorry.
Then
Yeah.
you
You're
can't
right.
conclude.
Correct. Right. So I cannot conclude. Sorry. So this is a false statement. Yeah. So I cannot conclude. Thanks. So it's just f of 0. So we don't need the value also. You're right. So it's just f of 0 over here. Okay. So f of xn converts to f of 0. So what I'll do now? So what I have obtained. So let's say this is 1. This is, let's say, 2. And this is, let's say, 1. Okay. So 1 tells you that f of x is equal to f of xn, okay, for all n belonging to n. Now you just pass the limit. So this will imply that f of x, so I'm just taking limit, okay, so taking limit as n going to infinity, we get f of x is equal to f of 0, right? And this is what we wanted, right? So since I chose x to be arbitrary, like it can be anything between minus 1 and 1. So what I got is f of x, and it matches with f of 0. So this is true for all x belonging to minus 1 to 1. So this proves that the function f, what we started off, is a continuous function. Okay, is this clear? Okay, so now let's come to this problem. Okay, let's begin with this. So this is a very unique function. Okay, so this has a name also. So it's called Thom function. Okay, it's given on the name of the mathematician who found this function. Okay, so this is also called popcorn function and raindrop function, because if you look at the graph, it would look like that. Okay, like a popcorn popping out from the machine, or rain coming from sky, like that you will see. So maybe I can give you, so let's see what the function is first, then you will understand. So this function is defined on 0 1. Okay, so maybe in general you see that it's defined on open 0 1. Okay, so here I have particularly chosen f of 0 to be 1, but in general you can define f0 as whatever you want, but if you look Google it, I think you will just get open 0 closed 1. Okay, so how we define it? So if my x is a rational number, okay, then so that means x is equal to m by n. That is the form of rational number, right, where the GCD of m and n is 1. Since we are in 0 comma 1, this means that m and n are natural number, so we don't need negative sign. Okay, so if we have x as m by n, then you are defining this function as 1 by n. Okay, just like that. Now when x is irrational, then you are just putting f to be 0. Okay. So I mean, if you look at the graph, you can clearly see. So let's say it is 0, it is 1. Okay, so at 0 point it is 0, correct? At 1 point it is 1. Oh sorry, at 0 point it has been defined as 1. Sorry. Okay, so you can understand that at 0 is a rational number, right? And 0 can be written as 0 by m for any m. Okay, so that's why you have to define it in, like, you cannot make sense of this definition. Okay, so here m equal to 0 is not allowed, because m and are chosen to be from natural number. Okay. So that's why 0 is being dealt separately. So f of 0 is 1, let's say f of 1 is 1. Okay, now if you go close to 0, okay, then you will have either rational points or irrational point. When you have irrational point, then it is going to be 0, right? So it is 0 on irrationals, correct? Now when it's rational, you see, when you are taking a rational number near 0, then it is of the form 1 by n. Okay, so like uh, uh, so suppose let me take some example. So let's say that x, so this anyway I'll come to the solution, then I'll tell you. So suppose m I'm choosing to be 1, let's say. Okay, then 1 by n is in the neighborhood of 0, correct? So then the functional value is going to be 1 by n, which is very small. So suppose I'm taking n to be very large, okay, so that it becomes very close to 0, then the functional value will be very close to 0, right? I mean, this is how it will look. It will be very dense. But if I take, let's say, m equals to 2, okay, and if I choose m equal to, let's say, 3, okay, then what will be the value? The value will be 1 by 3, which is quite significant. But and this 2 by 3, so what will be the value? 0. Let's say 6 kind of thing. So it will be somewhere in the middle, so here, right? So here the functional value is going to be 1 by 3, so which is 0.3 kind of thing. So it will be lying here, right, somewhere. So the actual graph, if you see now again, so this is just kind of description I'm giving. So the way I am making you understand is kind of discrete. I'm taking discrete points, I'm taking precisely. But if you look at the graph, it would be more like this kind of, I mean, this kind of thing will be there. Okay, so I don't know how to draw it properly, but what I mean is like, so at, let's say, half, let's evaluate at half. So at half the value would be half, right? Because this is how we define. So this will be converging like this. Maybe I should write, so like this it will go this. Okay, so I mean, so at each point you will have this kind of value at rationals point. At irrational it is 0 here, okay, and if you, so you see a rational number would be like m by n. Now as you are taking n higher and higher, okay, this will be coming close to 0 0, like this. So the graph would be something like this. I don't know how to precisely draw it, but maybe you can look in Google and you can see how the actual graph would be. So I mean, I'm just drawing this just to make you understand that why it's called popcorn function or raindrop function. From here you can understand. Although I've drawn it very bad, it's not a correct diagram, but maybe it could be drawn using computer. By hand it's very difficult to draw, okay, but you can look at Google, you can Google it and you can see the function would be something like this. I mean, okay, so this is why it's called popcorn function or raindrop function. Okay, so now what we have to check is, so this is quite interesting function in the sense that if you look at the continuity of this function, what you will see is that it is continuous at every rational point and it is discontinuous at every rational point. So see how this property is quite interesting, right? It is continuous at infinite points, it is discontinuous at infinite point, and all those infinite points are dense also. Like, it's not something which is scattered. You know that rationals and irrationals are dense in real line, right? So it is dense, this rational and irrational point, but at one of the portion of the dense points it is continuous and at the other point it is discontinuous, right? So this is quite interesting and this is why this function is quite famous. Okay, so now let's go to how to prove it. Okay, so maybe how should I start? Maybe let's take, first let us prove the discontinuity because that would be easier to prove. So maybe my claim 1 would be, or let's say directly, so let us choose C from this 0, 1 intersection rational points, okay, intersection Q. So I am taking C from here, so I have to prove that f is discontinuous here. So what I'll do, again the sequential criteria I'll try to use. So I'll take a consider, so okay, so this would mean the first thing I should write is f of c. What should I do? Maybe I should deal with c equal to 0 separately. Okay, because okay, so let me deal with c equal to 0 separately. Why I am doing so? So c belong to 0 comma 1 means that c will be equal to m comma n. Okay, where with the same thing that m and n are the natural number and the GCD is 1. Okay, and this will tell me that f of c, maybe I should, this would imply f of c is going to be 1 by n. Okay, so this is, I am choosing some rational point which is from 0 1 except 0. Okay, now I have to prove that it is discontinuous here. So how do we prove? So we'll take that since c is in 0 comma 1 intersection q, so let us consider a sequence yn or xn in 0 1 intersection irrational. Okay, so I'll take irrational points, okay, such that this xn converges to c. This I can choose by density property. Okay, now f of xn, what is f of xn? You see, when x is irrational, I am saying f of x is going to be 0. So this means f of xn is going to be 0. Maybe I should write here p by q form, otherwise there will be confusion between n. Okay, so what I have got is that f of xn is 0, and so this will converge to 0. But f of c, what is f of c? F of c is 1 by q here, and this is not 0 for any q. Right, for any q you choose in the natural number, it is not going to be 0. So this proves, this shows that limit x going to c f of x is not equal to f of c. Right, this is what it proves. So we have got a sequence which converges to c, but f of xn is not converging to f of c. Right, so this proves that this limit will not be equal. Okay, so over here we are not saying that whether the limit will exist or not. I am just saying that limit, even if it exists, it is not going to be equal to the value, the functional value at c. Right, okay, so this is what it says. Okay, so this proves that, and hence f is not continuous. F is discontinuous at x equal to c. Now similarly you can argue for 0 as well. Right, so when c is equal to 0, you know what is the functional value? F of c is equal to 1. Okay, I'll just copy it. I just write in short. So consider xn belonging to the 0 1 intersection q complement, then f of xn, so such that xn converges to 0, then f of xn will converge to 0, right, but f of 0 is equal to 1, which is not 0. Okay, so whatever. So this shows that limit x going to 0, f of x is not equal to f of 0 and hence f is discontinuous at x equal to 0. Right, so the first part, one part is done, that it is discontinuous at rational points of 0 1. Right, so this is what we have proved. Okay, now let us try to understand how it is becoming continuous at irrational point. Okay, so we'll try to look at that. Okay, so now the proof is like this. So what I'll do, so I'll again do the same thing what I was doing here. So like c I'll choose. So now the c, let us take c from 0 1 intersection q complement, right? And this will tell me that f of c is equal to 0, because this is how we define the function. Okay, now what I have to do, I have to estimate. So let me write what is the goal. Okay, so first let me write that I'll have to choose some epsilon be any real number. Okay, now the goal would be, what is the goal? The goal would be that f of x, right? So maybe to find, first let me write delta. So to find a delta greater than 0 such that this f of x minus f of c, f of 0 is 0, right? So f of c, which is 0, so I'll just write mod of fx. Okay, if you want I can include f of 0, f of c. This I have to say that this is going to be very small, right? This is less than epsilon if mod x minus c is less than delta. Okay, okay, so now you see how will this difference look like. So we have to check how this difference look like, then we'll go to the solution. Okay, so let me first write this. So this is something that we want to prove. Okay, now let us look at this difference. So this difference, if suppose I am choosing x to be irrational, then this difference is going to be 0, right? Because f of x is also 0. So this difference is going to be 0 if x belong to 0, 1 intersection q complement, right? But if my x is rational number, so suppose if x belong to 0, 1 intersection q. Okay, now when I write x belong to 0, 1 intersection q means that this means that is x will be equal to p by q. Okay, where p, q belong to n and GCD of pq is equal to 1. Okay, this is something I am assuming. So instead of writing this, now I'll write this. If x equals to p by q, where pq belong to n and GCD of pq is 1. Okay, maybe I can, if you want, let's put one restriction, belong to 0, 1. Okay, okay, because if I, this 2 by 1, this is also of this form, right? Or 2 by 3 if I write, then this is also of this form, but it's not in 0, 1. So that's why I am putting this condition that it should be in 0, 1. Then in that case what you define is your x, the functional value would be 1 by q, right? This is why, this is how my function is looking. Okay, and then my goal is that I want to prove that this is less than epsilon if, so see, this condition is anyway true, so we don't need to worry about this one because it is 0, so no issues. So this will be true, I mean this is less than epsilon if my x minus c is less than delta. So if it is rational, then there is no issue. So let's worry, so we need to only worry about a rational point, not irrational point. So this would be less than epsilon if my x, which is p by q, okay, and minus c, if this thing is less than delta, then we are done, right? If my p by q is very close to c, okay, then we can say that this function, I mean, and this difference is less than epsilon, then we can say that the function is continuous in this at c, right? So we have to find this delta, right? You remember the goal is to find this delta such that this 1 by q is very small. Okay, so I am again repeating what we have to do. So we have chosen some irrational point. Okay, so maybe, so I chose this c which is irrational, okay, belong to q complement. Now I have to determine one neighborhood. Okay, in this neighborhood you see there will be rational number also and irrational number also. Okay, when x is a rational number, irrational number, then there is no problem, it is 0, no issue. But when x from this neighborhood is rational, so from here let's say it is p by q form, then I have to make sure that this p by q, okay, so from here the functional value would be 1 by q. then I have to make sure that this I can make it very small, as much as I want. So, okay, so depending on epsilon I'll get this delta. This is c plus delta, c minus delta. Okay, so again I have to find a neighborhood. So first let's say I am fixed the epsilon. So epsilon, let's say I know, okay, it can be anything, so but I know it, the value of epsilon. Okay, then my goal would be to find a delta, so that if I'm in that neighborhood, if I'm in delta neighborhood of c, then my function value is going to be less than the value of epsilon. Okay, the usual thing. Okay, now let us try to understand that how can we make this 1 by q small. There is one thing that we know, that 1 by q, like, it's kind of, if I try to choose q very large, then obviously it will go to 0, right? So I have to somehow tell, okay, that the, so I have to somehow, okay, so I have to somehow tell that this region, okay, p by q, which are lying in this region, okay, this q is very large. That means this is greater than equal to some, let's say, n naught. If I can say that all the rational which are lying in this domain, okay, the denominator is large, okay, or in sense that, yeah, it is greater than equal to some value, then obviously 1 by q will be, so this will imply that 1 by q is less than equal to 1 by n naught. And by this, so this n naught is something that we have to find. Okay, so when epsilon is given, I can find, so this n naught I can find such that this is less than this one. Okay, so now, okay, so let me write in words again, then otherwise you will be confused. So see, epsilon is given to us, right? By Archimedean property we know that I can find, so there exists n naught such that 1 by n naught is less than epsilon. Okay, so this epsilon was given to me. So suppose you gave me epsilon, so let's say you gave me some epsilon equal to half, let's say, then from there I can say that, okay, I have n naught equal to 3 such that 1 by 3 is less than half. Okay, so this is by Archimedean property. Now this one n naught I have, since you gave me epsilon, I know there is some n naught, so I know this n naught as well. Now my goal would be to find a delta neighborhood, right? C plus delta, C minus delta. Okay, so that whatever rational is there, so p by q, rationals which are here, the q, it should be greater than equal to n naught. So this is something that I have to find. So I have to find a small neighborhood. Maybe this delta will not work. Maybe I'll have to choose a smaller delta. Maybe much more smaller. So you have to choose a smaller delta, so that you know that there will be infinite rationals, right? Because it's dense, so there are infinite rationals in whatever neighborhood you choose. Okay, so there are many irrationals over here, but I have to make sure that the rationals what we have here, the denominator is greater than equal to n naught. Okay, so once we do this, then we are done. So this is the only task, that we have to find a delta such that all the rationals sitting here satisfy this property. Did you get the idea what we are going to do? Tell me, because now we just have to write in words, that's all. So if you have understood, then I'll try to write it up. Okay, so now you can tell me if you are facing some issue in understanding this. Is this okay, or do you want some again, like, should I repeat it? Okay, it's okay. Okay, now let us try to write in words then. Okay, so now I'll just rub this off. So I've chosen epsilon greater than 0, any real number. So now by Archimedean property, there exists n naught in natural number such that 1 by n naught is less than epsilon. Okay. Okay. So what we have to do is now, so I'll just try to use, maybe should I write break the proof, or let me see if I can continue. So see, let us try to understand. So what I was telling you, that in this neighborhood you want infinitely many rationals. So if you can prove that after this domain there are only finitely rational which are satisfying this property, then we are done. Okay, so maybe let me write it as a claim, then it would be easier to understand. So let me put it here. Okay, so what I'm trying to say, let me write in words. So suppose for you have some natural number, okay, so for n belonging to this natural number, I'm saying that there will exist finitely many rationals. So maybe x equal to p by q, which are in 0, 1, and such that again the same thing, like what should I write? So GCD of p by q, pq is 1. Okay, they exist finitely many this such that q is less than equal to n. So what I'm saying, I'll again tell you in words. So suppose you give me any natural number, okay, so this is any natural number you give me, okay, corresponding to that natural number, so I can find, so let's say this is 0, 1, okay, so suppose you gave me some natural number n, corresponding to that natural number I can find that there are only finitely many rationals, okay, there are only finitely many rationals such that the denominator, okay, this is less than equal to that natural number. That means, in other words, over here, okay, let me just stick to this point, then I'll come to the next conclusion. Okay, I mean this will eventually solve the problem, because you see, if you have any C point here, then since there are only finitely many rationals which are whose denominator is less than equal to n, then suppose this was my C, then I will leave these points, okay, these were the points, so I will take a neighborhood like this, okay, and in this neighborhood all the rationals p by q which are here, the q is always greater than equal to n, right? So this will prove, I mean this will help, this will eventually prove the result. So the only task is to understand this claim. Once you prove this claim, then everything is done. Okay. Okay, so now let me prove this claim. Okay. So let us look at how the number is. So suppose here I have to take q equal to, let's say I'm taking q equal to 1. Okay. So suppose q is equal to 1. Now x was my p by q. Now if I want this p by q to be in 0, 1, so there is only one choice. So this belong to 0, 1 if p is equal to 1. Because if I take any p which is not, I mean if I take p equal to 2, 3, then it is not in this domain. So p is equal to 1. Okay. Suppose if I take q equal to 2, then x equal to p by q will be in 0, 1 only if, like for example, if p is equal to 2, then it's there. If p equals to 1, then it's there. So if p belong to 1, 2, right? That is the only choice that we have. Correct. Similarly, for q equal to 3, you see x barabar p by q will be in 0, 1 if p belong to 1, 2, 3, right? Because 3 is the maximum number what you can get. Once you exceed 3, this p by q will be greater than 1, right? So in the same way, if you take q equal to n, okay, then x equal to, so for this q, x equal to p by q will belong to 0, 1 if p belong to 1, 2, till n, right? Okay, so what we have got, what we have understood from here is like, so for q, sorry, so we are looking for rationals whose denominator is less than equal to q. Now what we saw is, like when we take q to be less than, if you want this denominator to be less than equal to n, then you see we have only finitely many choices for p, right? So for q less than equal to n, we have only finitely many choices for p, so that p by q belong to 0, 1, right? And this proves the thing what we wanted to prove. I mean, finitely many choices for me p means that finitely many choices for x. Right? So this proves the claim. Is this clear? The proof is, I mean, it's not difficult, it's very easy. But the only thing what you have to understand it properly. So what I am saying, again I am repeating, what is the meaning of this claim? So this claim tells you that if you give me any natural number, okay, I'll get only finitely many rationals for which the denominator is less than equal to n. Okay. Okay, so now this was the claim, then this is done. So now what I was saying here, that if I choose any epsilon to be any real number, then by Archimedean property I'll get this n naught such that 1 by n naught is less than epsilon. Okay, now by claim there exist finitely many rationals in 0, 1 rationals, or there exist finitely many x बराबर p by q into 0, 1 such that q is less than equal to n naught, right? So now let's say let us denote those rational points. Okay, so these rational points, those rational points as x1, x2, x3, let's say till xk, right? So there will be only finitely many such points, so I'm denoting it by this x1, x2, x3, xk. Okay, now so again I'll repeat the same thing. So suppose this was my 0, 1, and let's say this is my c. So it has, c is irrational, right? R minus q. Okay, now these, let's say x1, x2, these are like this. So now I'll choose my neighborhood delta. So now I'll just write choose delta greater than 0 such that c minus delta and c plus delta intersection with this set x1, x2, xk is equal to 5. Okay, so this I can always do because there are only finitely many xk's. Okay, so this is very important, that there are only finitely many, that's why we can do this. Okay, choose delta such that this happens. Then if then x how should I write, then for x belonging to c minus delta, c plus delta intersection q. Okay, so let me write it as in the form of p by q. So for x equals to p by q. Okay, so when I'm writing p by q, this gcd pq equal to 1 is already there. Okay, so I'm not writing it again and again. Then for x which is lying here, this q, what will q satisfy? That q is always greater than equal to n naught, right? because in this neighborhood these xk's are not there, and these xk's are not there means whatever rational we have, the denominator is greater than equal to n naught. This is what we get, correct? So now let's come to this, what I was initially writing. Okay, so this is, let's say this is star. Okay, now for x belonging to c minus delta to c plus delta. Okay, if you look at fx minus fc, this is equal to mod of fx minus 0, right? So this is equal to 0 if x is irrational, right? And if it is rational, then I'll have 1 by q if x is equal to p by q, which is belonging to q, right? This thing, right? And now what I know is this 1 by q is greater than equal to n naught. So from here what I can say is 1 by q is less than equal to 1 by n naught, right? This is the obvious implication. And 0 is anyway less than equal to 1 by n naught. So what I can say is this is less than equal to 1 by n naught, correct? This is by star, maybe you can say, right? And now I know this is less than epsilon. This is how we chose this n naught. Remember? Did I write? Yeah. So maybe this, let's say this is 1. Let's say this is 2. So this is by 2 and this is by 1. Okay. So what we prove is that fx minus fc is less than epsilon when I chose delta, so which was chosen from by the lemma. Okay, so we know that there will exist some delta. Okay, so this proves f is continuous at x equal to c. Okay, is this okay? So the main thing in this proof is just this, understanding this claim. Okay, once you understand this claim, there is nothing in this proof. Do you have any doubt? Okay. Okay, so then actually I was supposed to discuss one more problem, but anyway, like time is, we don't have much time, so I'll stop here. But maybe in the next session I will try to do this problem also. This is something that we have, this property you must have seen in one of the assignment, like I think last session or last to last session, somewhere we have discussed this kind of function. And then some of you told that this it implies that the function is linear, right? This kind of thing, but okay, we'll see, check in the next session maybe. Okay. If you want, you can try this out. If you are able to do it, very good. Otherwise, I'll discuss in the next session. Okay. Okay, then that's all for today. See you next week then. Okay then, thanks. Bye.